Assalamu alaikum. Today we'll discuss lecture number 5 of digital signal processing, which is fast Fourier transform. Let's quickly recall what discrete Fourier transform was. Fourier transform helps to convert time domain signal into frequency domain signal, and discrete Fourier transform convert discrete signal which is periodic into frequency domain signal. It is its formula. We know that number of additions in discrete Fourier transform is equals to n into n minus 1, and number of multiplication is equals to n square. Number of multiplication is much more greater than number of addition. Meanwhile, number of multiplication cost is 25 times than addition, which is much more. We need to define a technique which will reduce our computational cost. So we'll use fast Fourier transform, that is FFT. Let's quickly check how this method was derived. We know that x of k was equals to x of n into e raised power minus j 2 pi k n by n. We replaced e raised to power j 2 pi k n by n with this number. Okay. So we split it the even and odd parts of the whole term. We let n is equals to 2r and put that in both equations. Here we know you can see that we put 2r plus 1, which shows that it is odd number. Meanwhile, we did some work over here, and final equation was a of k plus wnk b of k, where bk is odd number and ak is even number. So let's take an example. X of n is equals to 2 minus 4 3 1 minus 2 0 3 1. So we'll split this whole signal into even and odd composition. So make sure you do it right. Don't take the number as the reference. Take the index as reference. That is 0, 2, 4, 6. They are the even numbers, okay? Even index numbers, okay? Meanwhile, minus 4, 1, 0 and 1, they are odd index, okay? Now it is 4 point discrete Fourier transform. First we will apply some DFT technique and then we'll use FFT technique, okay? So the formula for DFT, and we did some calculations over here. You can see you'll definitely have a question in your mind that if we did the same thing as DFT over here, what was the purpose of saying that it is odd FFT? Where you can see we used n is equals to 0 to 3. Now for odd numbers we again started from 0 to 3. It is not from 0 to 7. So it's a bit easier to do this, and it is a bit less costly. You will see further more. Okay, we completed our calculations here, and then you should look at the circle. This shows this is an important thing you need to know in FFT. We divided the circle into 4 parts because our signal had 8 samples. We divided it in the 8 parts. Okay, so every pi shows one value. For W8 of 0, W8 of 1, make sure you move clockwise. 2, 3, 4, 5, 6, 7. Okay, so here it is. There are even samples and there are odd samples. We got these answers by DFT for the even samples and these answers for the odd samples. We'll draw horizontal lines for every one of them. Then we'll connect first odd sample with the first or even sample, and then we know the formula A of k plus W n k B of k, where B of k is even sample and A of k will be the odd sample. So first A of 0, which is 6, minus 2, which is B of 0, and into W8 of 0. And we know from this circle that W8 of 0 is 1. So 6 minus 2 is equals to 4. Meanwhile, W8 of 1 is this term. So we multiply this term with odd number, which is minus 4, and we added into the even number, which is 4, and we got this answer. We did this whole thing with DFT and we got the same answers. Okay, after doing these 4, we'll move these odd numbers down there. This minus 2 and 6 will be moved here. You can see it makes a butterfly shape, and it is called a butterfly method. And it reduces the number of additions and multiplications. Okay, we will do the same thing, but make sure you don't confuse it with this, that when you move a line over here, it means you are multiplying this factor with something that moves some over there. You're always going to multiply this factor with odd number. Okay, so again, multiplications, additions, and you got the answers. They may again, I'm saying they are the same answers we got for DFT. Okay, so you will ask why we needed another method when we had DFT. Even we applied DFT here for finding these values. Okay, we got an advantage. We reduced the computational cost. We reduced the computational cost by reducing the number of additions and number of multiplications. In DFT, the number of additions were equals to n into n minus 1. But here you can see we added only 8 times. Only one addition, one addition, one addition, one addition here. And there were 8 lines, and we added 8 times. Meanwhile, there were 8 multiplications. Okay, so first we'll find the number of additions which we had in DFT, because we did 4-point DFT for finding these values. Okay, so 4 into 4 minus 1, which is 3. For this section it will be 12, and for this section it will be 12. So we multiplied 12 by 2 and we got 28. So we made some other additions in here in butterfly shape, so we added that 8 and we got 32. Let's compare it with the number of additions from DFT. There were 8 samples total. 8 into 7, 56. 32 is much more less than 56. Multiplication, n into n. Here we have 4n. Okay, 16, and we have 2 boxes of 4n. So 16 into 2, 32, and there are 8 multiplications over here. There are 40. Okay, for DFT there were 8 samples, and 8 into 8, 64. 40 is much more lesser than 64. Now let's do the whole thing with butterfly method. There is divide. First of all, divide even and odd numbers in one point DFT. Okay, even, odd, even, odd, even, odd, even, odd. Then do the butterfly method. You got the answers same as we did before. Again, it becomes 2-point FFT. Again, do the butterfly method and you got these answers. Again, a bigger butterfly, and you get what you wanted. Okay, when you are doing 1-point butterfly, you will divide your circle in only two halves, this half and this half. W8 of 0 will be 1 and W8 of 1 will be -1. When we will doing two point DFT, you are going to divide your circle in 4 halves. W8 of 0, W8 of 1, 2 and 3. Values will be changed, and when you will do the 4 point DFT, you will divide it in the 8 parts. Okay, so again we are interested in finding how much we got benefited by this method. So here is the key. Number of additions are 24 and number of multiplications are 16. So meanwhile, that's how we decreased number of additions and multiplications from the previous method, that was 32 and 40. So that's how we decreased using this function. That was all from lecture number 5. See you in the next lecture. Khuda Hafiz.